Alright, we're right where we left off. Objects 1, 2, and 4 will travel equally as far since they slide instead of roll. And the reason that this is important is because if they slide, so all of their kinetic energy is translational. If all their energy is translational, then they all end up with the same linear speed at the end of the ramp. And since they're all going to take the same amount of time to fall, they will land the same distance from the table. Okay? They all have just translational kinetic energy. They will all have the same speed at the end of the ramp. They're all going to take the same amount of time to fall. Therefore, they will all go the same distance for 1, 2, and 4. However, objects 3 and 5 roll down the ramp so some of their kinetic energy is rotational. Meaning they're translational K and therefore linear speed V won't be as high. Now I do want to point out at this point that the total kinetic energy for each of these objects is the same. The total kinetic energy is the same for 1, 2, 3, 4, and 5. The reason we know that is because they all start with the same amount of gravitational potential energy. So all of that becomes kinetic energy at the bottom. It's just that for 1, 2, and 4, the kinetic energy is purely translational. For 3 and 5, it is translational and rotational. And since we are splitting the kinetic energy for 3 and 5 into two parts, only one of which really has to deal with linear speed. The ones 3 and 5, they just won't travel, they won't have as much speed because we're splitting it up. But the total kinetic energy is the same. That does not change. So, therefore V won't be as high. Therefore, even though they take same amount of time to fall as 1, 2, and 4, their lower speeds, and by this we mean V, mean they won't travel as far from the table. The student was right about all of that, okay? The student correctly realized that the amount that the rotation meant that some of these objects would not travel as fast, therefore they wouldn't go as far off the end of the table. Which parts, if any, of the student's reasoning are incorrect? There is something that they're incorrect about, okay? And it comes when they say that objects 3 and 5 travel the same distance as each other. So the student is incorrect. In saying that 3 and 5 travel equally as far. Now, he was right that they will not travel as far as 1, 2, and 4, but the student said 3 and 5 will travel the same. And that is not true. The reason it's not true: these objects do have the same mass and the same radius, but they do not have the same shape. A fancy way of saying that is the mass distributions are different. Why does this matter? Consider a ball, essentially a sphere, where we're talking about 3 and 5 here, right? A ball, and it says it doesn't say anything about a hollow ball, it just says a solid ball, okay? There we go. And we have a cylinder, a hollow cylinder, okay? They have the same mass, they have the same radius. Which object has, on average, the mass being closer to the axis of rotation? The axis of rotation for both of these is through the center. The ball has more mass located closer to the center. The hollow cylinder, all of its mass, if it's hollow, is located on the edges. That's really far away from the axis. Remember that for objects, if their mass is really spread out from the axis, that contributes to a higher moment of inertia. This will have a higher moment of inertia than the ball. The ball has mass that is close to the center of the axis of rotation. The hollow cylinder does not. So because their mass distributions are different, this causes, even though mass and the radius are the same, the coefficient part of the moment of inertia is going to be different. Okay? So this causes different moments of inertia. So, it is easier, and I'll put that in quotes, to get one object, in this case the ball, to move or rotate than the other, the hollow cylinder. And because of this, because it's easier to get the ball to move or rotate than it is the cylinder, therefore, the ball will roll faster. It will pick up more speed. And therefore, ultimately travel farther than the hollow cylinder. Again, not a result I really would have predicted before learning about this, okay? Actually, I'm pretty sure I did learn this at some point in college, but it had been so long since I had actually used something like this. When I first started teaching AP, and I first started going through this stuff, this was brand new to me. Or, well, it felt brand new to me, and it was neat to relearn this stuff, okay? the ball will go farther than the hollow cylinder because it has a lower moment of inertia. Therefore, it's easier to get the ball to move and rotate. It will pick up more speed. It will travel farther than the hollow cylinder. Okay? Now, that's a lot of words. Okay? Right now, this is probably very hand-wavy. What we're going to do now is we're going to see exactly how far all of these objects will fall. If you flip to the back, there are some numbers for you. We're going to calculate, okay, well, based on this, how far will everything actually move? This would be a great experiment to do in class. I would really like to do this someday. And to see this actually work in action. Okay, so this tells us the rotational inertia for the ball, for a ball and a hollow cylinder, respectively, are I equals 2/5 mr squared. We've done that before, and I equals for the cylinder mr squared. If the length, and which length is this? I believe this is the length of the ramp is 3 meters, the height of the ramp is 1 meter, and theta is 30 degrees. We want to find how far they move for each situation. Let's do the easy ones first. Let's do the ones that don't roll. That would be 1, 2, and 4. This should be very easy for us, okay? 1, 2, and 4, we can figure out how fast, or we can figure out how far they move if we know how much time it takes them to fall from the table to the ground, and we know how fast they were moving. So here's what we need to do. In order to figure out how fast they were moving, probably the easiest thing to do if we don't want to get into forces and free body diagrams and everything, we could use energy. We start with ET equals ET. For 1, 2, and 4, the ones that don't rotate, the ones that don't roll as they make their way down, we know that at the top, okay, they had gravitational potential energy. And at the bottom of the ramp, they have kinetic energy. And since they slide, this is purely translational kinetic energy. So, we have their gravitational potential. We know that's mgh. Oh, h, oh, okay, I see. H, I forgot what I made h. So, let's see, here's a picture. Okay, we're only given L and the angle. We need this height, right? We need how big that is. That's not this. This is, I know I'm writing over everything right there. That's that. We need to know what this is. I guess I'll call this, well, I guess it would be L sine theta, right? So we have mgh equals 1/2 mv squared. Let's cancel these. H is L sine theta, 1/2 v squared. If we solve for v, we should get that the velocity at the end of the ramp, there we go, is radical 2gl sine theta. Okay? Now, that's how fast it's moving at the bottom. I said we also need the time. We also need the time that it takes for it to hit the ground. We can get that by using the y variables. Initially, based on the way it rolls off, there should be no initial speed in the y direction. That must be 0. We could also say that let's say since it hits the ground, the final y position is 0. The initial y position is h. Okay, 1 meter. We'll plug that in later. Initial y position is h plus 1/2. Let's see, if we're going 0 is at the bottom, h is up. That means up must be positive, so we have to put in a negative g t squared. Let's see, bring the h to the other, or no, we bring this to the other side. We solve for t. We should end up with t equals, I believe, the square root of 2h over g. That's the time it takes for every single one of these to hit the ground. Is it every single one? Yeah, it is every single one, okay? They all take the same amount of time to hit the ground for all 5 objects. Now, 1, 2, and 4 are all going to land the same distance, we said. We have the time, we have the speed. All we have to do now is figure out, well, how far do they go? Let's say that they all start at the same position of 0. And we know that projectile motion, objects will not accelerate in projectile motion once they're in the air. So the position is solely dependent on the speed they have when they get off the ramp, 2g L sine theta, times the time, 2h over g. We can combine these. If we're multiplying radicals, we can combine them into one big radical. So this would be, let's see, 2 times 2, 4g L sine theta h over g. A couple things can happen. My g's cancel out. Square root of 4, we can bring that outside, is 2 L h sine theta. All we do is we plug in our values. We know that L is 3 meters, h is 1 meter, sine theta, I believe it was a 30-degree angle on the ramp. Let's see, I did all these calculations before. X turns out to be 2.45 meters. Okay? For the objects that slide, they should land about 2.45 meters away from the edge of the table. I'm going to stop there.